A linear transformation from Rn to Rn scales the volume of any region in Rn by the same factor. Let's call this the volume scale factor of the transformation. Since the volume scaling is isolated in the sigma factor of the singular value decomposition of A, we can say that the volume scale factor of the transformation is the product of the singular values. The orientation factor of a transformation is 1 if the transformation preserves orientations and -1 if it reverses them. We define the determinant of a transformation to be the product of its volume scale factor and its orientation factor. The determinant of a 2x2 matrix ABCD is AD minus BC. The formula for a 3x3 matrix is similar, though there are more efficient ways to calculate the determinant than using this formula. You'll generally defer this task to software. Determinants can be used to check invertibility, since a matrix is non-invertible if and only if it maps Rn to a lower dimensional and hence zero volume space. When we deal with real-valued functions of a real variable, we develop symbolic rules of calculus to help us solve problems, such as optimization problems. Likewise, we'll develop symbolic differentiation rules for expressions involving matrices. If f is a function from Rn to Rm, we define the derivative of f with respect to the vector x to be the matrix that you get by differentiating each component of f with respect to each component of x. With that definition, we have the following rules. The derivative of a linear transformation of x is just that linear transformation. If x appears as x transpose on the left side of A, then the derivative is A transpose. The product rule looks very similar to the product rule for ordinary functions. For example, if f of x is x transpose ax, then we can apply the product rule and find that the derivative of f with respect to x is x transpose times the sum A plus A transpose. Let's see how this looks written out. Let's try this on a real problem. Consider these 5 points in the plane. Let's look for the line y equals mx plus b, which minimizes the sum of squared vertical distances to these points. We can write the function we're trying to minimize in terms of matrix multiplication as follows. Differentiating and setting the result equal to 0, we get, since we know that the rank of A is 2, the rank of A prime A is also 2, so we can apply A prime A inverse to both sides. Plugging in the actual numbers from this problem, we find that the slope of best fit is 1.9 and the y-intercept is -5.6.